trait-based methods to classify planetary types. First, we use the original dataset that includes missing values. Then we impute the datasets using the known values. And here, so here is like the left, the trait-based methods based on all of the features. On the right, it's only based on the important variables that that we are gonna use to improve our accuracy. So first we load the dataset. It's the clean 5 to 72, and we define features and target. Features here are all of the on the left are all of the features in the dataset, and target is planet type. However, the features on the right only includes the important variables. Then we encode the categorical features like the spectral, like the stellar spectral type and the stellar metallitic ratio. And since the original datasets have missing values, and so random forest and gradient boost and some other trait-based methods are not supported because they don't support missing values. So here we try the histogram gradient boost, which allows missing values. And we define the search grade, which has 4 dimensions: learning rate, max iterations, max depth, and L2 regularization. We trained the model. It took a while, and the results are somewhat similar. As you can see, if we use the only important features, the test accuracy improved by, I think there's only one example. Like it classified one more example correctly. And here's I propose a method to visualize the hyperparameter tuning. So it's like the CT diagram in hospital. It's like we set 2 dimensions of the tuning parameters to be 0. So now it becomes a cross section of the 4-dimensional tensor here. And we compute the confusion matrix. So the first means the gas giant. The second row means Neptune-like. Third means super Earth, and the last row means the terrestrial. Oh no, sorry. The last row means unknown. Second to last means terrestrial. And then we try the extreme gradient boost. Brian also tried this, and we have a consistent results. So one more. So gradient boost offer the feature importance information, and I rank that feature importance. So it turns out the planet radius seems to be most important, then followed by the planet mass. On the right is basically the same, only we use the important variables. And by using the only important variable, we seem even increase the prediction accuracy a little bit. Here's the same. So it does confirm this graph that most of the variables are not very useful. The original dataset that contains missing values for classification. It is overall good, but it's only limited to some classification methods. So we decided to impute our data in order to make our problem be supported by more classifiers. So here's the imputation details. First, we reduce the number of types in the stellar spectral type. Originally, there's a lot, but they can be simplified into seven labels, ranked from the brightest star to the dimmest star. Actually, it's the bluest star to reddest star, but whatever. And also encode categorical variables. And here we use the KNN imputer and choose the number of neighbors equals to 2. So why did I choose 2 here? It's because was later verified by the Kepler's ratio. It turns out if we choose a large number of neighbors, the Kepler ratio turns out to be large. So what is Kepler ratio? So from high school physics, we got to know that the planets period square over the semi-major axis cube and times the stellar mass will be a constant that's only determined by the gravitational constant. So the imputed data are expected to be as close to the Kepler law as much, right? So I tuned the number of neighbors parameter by observing the Kepler's ratio. And it turns out we cannot choose a very large number of neighbors. Otherwise, the ratio, the variance of the ratio will tend to be a lot more. So the imputation has a sequence. So first we impute orbital features because we think they tend to be there tend to be more dependency in the orbital features. And then we impute the planet features like the planet radius, planet mass, and the planet type. And then, and the last, we impute the stellar features, include.
Hello everyone, my name is Karthik, and I am going to be going over the unsupervised section of the exoplanets analysis, and mostly I'm going to be talking about k-means clustering and trying to see how the clustering works by comparing it against the original labels, namely the planet types. And for this clustering section, we cannot have categorical variables. We can encode 0 and 1, but because it's distance based, we decided to choose just continuous variables. And out of the 20 odd variables, we chose 10 variables that are continuous in nature, and the 11th variable is the planet type, which is used to verify the clustering efficacy. And clustering, k-means clustering cannot have missing values. So most of the values are dropped from the data set, and we are left with about 648 data points and 11 features, where one feature is the planet type. So we have like 10 features for clustering. And clustering is also pretty sensitive to outliers. So we just remove any data points that are 3 standard deviations above the mean, and about 40 odd data points are removed, and that leaves us with 605 data points. It's not a huge data set, but I think it's sufficient for the purposes of we are iterating here. And before we go over the clustering procedure, we just have to check the distribution of the dataset, because as you can see, most of the variables, some of the variables are really skewed in nature, namely the orbital period, the planet mass, and the distance to the stars. And this is the standardized version, because clustering requires standardization, and the features have to be around mean 0 and standard deviation of 1. We just like standardize the dataset, and the histogram looks like this. And in order to get this somewhat looking like a normal distribution, we are going to take the natural logarithm of some of the variables and see like how the distribution looks like. And after taking the logarithm, the skewed nature of the distribution is somewhat changed to a normal distribution. And after standardizing, the distribution of the features looks like this, with mean 0 and standard deviation 1. And we fit this into the clustering procedure, and we try different methods. First, we're going to fit the original features without any transformation, any log transformation, and see how the model is going to perform. And for the purposes of this analysis, we are going to be just choosing 3 clusters, but the analysis of the silhouette score, which basically tells us how a single data point is classified, is basically clustered within the same cluster compared to any neighboring clusters. So the silhouette score varies from -1 to 1, 1 indicating that most of the data points are within the same cluster, and like the adjacent clusters are far away, which is what we want. And the silhouette score for clusters 2, 3 are somewhat in the 0.3 range, and it starts declining from there. So it's saying that there are probably around 2, 3, 4 clusters based on the features we are feeding into the model. But for the purposes of this analysis, we are going to just be looking at 3 clusters, because there are 4 different planet types with respect to the 605 data points we have, and one of the planet types is terrestrial, and terrestrial is just about 8 data points. So ignoring that, we can just assume that we have 3 clusters, and we're just going to be comparing how the 3 clusters perform with respect to the original labeled planet types. So yeah, and here you can see we just have like 8 data points for the terrestrial planet type in the 605 data points we have, and our clusters with the original data set is saying like there are 309 data points for label 1, 291 for label 2, and for label 3 it's just 5, and the plot looks like this. So this is the original planet types with respect to the planet radius and log of the planet mass, which is in Earth masses, and you can see like distinct intersections where like the blue is super Earth, green is Neptune-like, and the orange or the brown thing is gas giants. And our clustering algorithm with the original data without any log transformations, or PCA, gives us this clustering, this clustered set of data points, where you can see it's not like perfect, but you can see some distinct regions, and most of the data points are mixed here. And label 3 is just 5 data points, so it's not doing a good job. So let's just proceed to the transformed data set, where we transform the original data, like some of the features in the original data, by doing a natural logarithm, and we get a silhouette score that looks like this. So it's basically deteriorating. If you just have like 2, the silhouette score is 0.4. But just barring the silhouette score, if you look at the clustering clustered data points from the log transform dataset, it's much better visually, because it's the number of data points in label 3 is much more than what we had in the previous procedure, where we had just the original dataset, and the number of labeled data points like is somewhat closer to the original planet types. For label 3, we just had 5 data points, but here we have like 100, which is similar to the super Earth. and the cluster set of data points is still not perfect. We have mixed results. So, and probably one of the reasons that we have such a bad results on the Silhouette score is because we have 10 dimensions, and as we know, k-mean suffers from the curse of dimensionality. And for this, maybe we can reduce the 10 odd dimensions to 3 or 4 by doing a PCA. And doing a PCA gives us this plot where it says that having 3 components explains about 82% of the variance in the dataset. So we just choose 3 components for now and fit the k-means algorithm with respect to those 3 components. And the PCA clusters look like this, but most importantly, the Silhouette score is much better compared to the log transform dataset. So we have about 0.35, 0.34, etc., which is similar to the original clustering performance. But if we look at the plot, it's similar to the log transform dataset, but the Silhouette score is much better, and we can see like the labels are somewhat closer to the original labeled dataset. So I think like doing a PCA reduces both the computational complexity and also increases performance. And I think doing a PCA before fitting the k-means algorithm is fruitful for this purpose. And just visualizing the PCA in 3 dimensions, we have these clusters. So these are the red, purple, and the green labels, and these are the clusters with respect to like the PCA components. But if we look at the original labels, it's somewhat mixed. Sorry. Yeah, so it's somewhat mixed. And it's not as distinct, but because it's just based on these 3 components, and the original data types can be original planet types can be anywhere in this, and it's expected that it need not be perfect. And looking at this plot in 2D gives us this, which is basically the cluster, the R clusters with respect to 2 components, 1 and 2, which is principal component 1 and principal component 2, and these are the loadings, which basically gives us the correlation of each of the features, like the 4 features we have here with respect to the principal components. And it says that the orbital period is correlated with component 2, and the distance from the star and the planet mass and the radius are correlated with respect to component 1, and it is like negatively correlated, and that's why the arrows are in the left direction. And looking at the plot in 2D, this is the original planet type clusters. It's not like perfect with respect to component 1 and component 2. Like the clusters are not distinct, but our algorithm classifies like these separate clusters, and it's expected there will be errors. Yeah, and that's about it. We also tried fitting the clusters on a subset of features, and we got results similar to the original dataset, not the log transform dataset, where it's just saying there are 2 clusters, and it's just ignoring the 3rd label. So yeah, I think like doing a PCA and then fitting the k-means algorithm gives us good results and balances both the complexity and the performance.